Dear students, welcome to this massive open online course on operating systems, and today we are going to see about kernel IO subsystem and IO streams. So, the various topics which we are going to discuss is about how kernel IO subsystem is used for by the operating system for handling input and output, and how it enables a device independency. Data is transferred from the application to the actual device, and also it identifies the various IO devices and the driver softwares which are responsible for handling this input and output. So, the data which is generated by the application will be given to the device by based on the device specific commands. The drivers will generate requests and it will be sent to the devices, and the various IO communication methods which we can adopt to reduce the overhead of the CPU. We discuss those methods, and we also discuss about buffering, caching and spooling mechanisms, which also enables the synchronization or the flow control mechanism which match the speed between data transfer rate or with the type of device which you are going to use. For example, if you have a printer, the printer is a mechanical and electronic based devices which takes a lot of time for printing, whereas the data generated by the application will be huge. So, we have to store that in the buffer, and then we use spooling method for printer. So, likewise we have various techniques, and we discuss about those techniques, how data is handled between the user application and the devices, and at last how this data is sent. For example, data is sent in the form of bytes, in the form of character, in the form of a group of in the form of streams. So, if you want to send data in the form of a stream, this data has to be handled in different way. So, we have a lot of frameworks for that. So, you have streams framework in Unix that can handle data which is of larger volume to send to any devices which consumes this data and produce the output. So, as a whole we can call IO in an operating system is the input and output which enables communication between the computer systems and the external devices. So, here we perform data transfer within the system components or from the system to the components which is connected in the internet or in the network. So, whatever it may be, we have to perform IO. This IO will help processes to fulfill its goal. For example, if you want to print a document, you have to send this content to the printer. If you want to view that in the screen, you have to send the content to the display device using the display through the display controller. So, likewise we have interaction between the devices and the application, and as we discussed, the devices include keyboards, printer, network interfaces, display screens, etc. So, the OS will hide the complexity of the underlying hardware which is responsible for giving this output from the applications. So, for example, you have generated an output. This output has to be displayed in the screen or has to be using a printer. So, ultimately the output is there, you have to print or you have to display. So, if you want to display, you have to click one thing, but ultimately it is for the user, it says that you have to print or you have to display, but what actually it does is it is sending the output to the device, that is all. The device has its own property of either printing or either displaying, that will take care of its job. So, this is how the interface is hidden. Interface helps in hiding the complexity of the devices which we use. Of course, we use device drivers that will act as the actual interface between the application and the device. It generates the corresponding commands that can initiate the proper functionality of the device. So, these device drivers will play that role, but as far the user is concerned, it is hidden. So, we have the kernel IO subsystem that is very much responsible for efficient and reliable as well as secure IO operations that can be performed between the user application and the devices. In that case, how this kernel IO can be managed. So, OS responsibility is IO management is one of the main responsibilities of the operating system, and how the kernel is carrying IO is what we are going to see now. We all know that different devices will have different speeds and protocols used for communication. So, we have a serial in data transfer, we have parallel transfer, synchronous, asynchronous, all these will play a major role. So, different devices with different protocols for communication. So, we have to handle all this type of communication, because the application can generate data, and if it wants to send to different devices will follow different types of protocols and transfer speed. So, if you allow the application to directly access the hardware, is basically it is not safe, because hardware control by the application is not that easy, and applications should be more aware of hardware commands. Straight away you cannot send and operate a hardware. We have to use basic API methods that can invoke a request, this device driver will in turn generate the respective code that can make the device perform its function. So, the OS will ensure the independency of the devices as well as how it can be protected and access control mechanisms can be embedded, and how efficiently we use the available resources. So, this is the main objective. So, for this we use the help of the kernel, which acts as an intermediary between the hardware and the user program. So, what is kernel IO? It is the core component of the operating system's kernel, which manages all input and output operations. So, it provides a uniform interface to various devices attached with the system, and it also handle devices of various categories, like a device which can handle only blocks of data, a device will handle only each character. So, we have different types of devices which accepts different types of data. So, the kernel is responsible for handling both variety, and also the main job is, my utmost purpose of kernel is to coordinate the device driver and the application to interact with the hardware. So, the goals are to have device independency, to increase the efficiency by minimizing the overhead of memory with CPU, and reliability, handling errors gracefully. So, if there is a small error, then it is not report without doing the functionality, which it can, there are capabilities which can handle the error. Concurrency is suppose if multiple applications are generating in output request, for example, printing, displaying, so on. So, all these should be handled concurrently. So, to increase the performance of the system, that is the one of the main goals of the kernel IO subsystem. Of course, we have to controlled access to all the devices to ensure security for the devices as well as the data which you want to send as an output. So, before that we discuss about various IO devices which we can classify them based on how they treat data. For example, if you send data one by one, that may not be efficient for devices which consumes large amount of data and store volumes of data, large volumes of data in the memory, like hard disks. For example, HDD hard disks and SSDs are devices which can store data in terabytes volume. So, in that case, if you send data one by one, it is not efficient, it takes a lot of time, already it takes a lot of time for storing the data. And moreover, SSD we already discussed in the other presentation, where SSD we have a concept called flash memory, which takes less time for reading and more time for writing. If you keep on writing with the small volume of data, then more writes will happen, that will affect the performance or the lifetime of the device itself. So, we have to transfer data in the form of blocks, we have to wait for the data to get accumulate to certain extent, then you can send as a request for writing. So, this is one type of devices where blocks of data will be treated as input for the device. The second is character devices. Here the data is transferred as streams of characters one by one. Example, keyboard. So, keyboard we have if you press a key, immediately the key will be displayed. So, if I press A is displayed in the screen. Similarly, mouse, if you move mouse, for each movement the mouse character is maintained. It is not like if you move a mouse to a half feet, then only the cursor, mouse cursor will move in the screen. No, even if you move little bit, the cursor is also moving little bit. This is called streams of characters, and serial ports where data is sent serially with lesser volume. So, we have second category, character devices. Third is network devices. Here we have data that is transferred in the channel through a network which having so many devices. So, with respect to a system, the data will go via the network interface card outside. So, in that case you have to form, of course, if you look at the network point of view, we have to convert data blocks into packets, then it forms a frame, and ultimately the frame is sent along the NIC. So, it has lot of bits to a considerable size. So, this is packet based communication. Of course, the packet based communication is they are talking about data in the network layer. So, as a whole, if the communication through network devices, we call that as packet based communication, which is possible through network interface card. So, we can classify IO devices in this perspective into three categories: block wise, or character wise, or network wise devices. Of course, we have controllers that controls the operation of all these devices. We call it as device controller that controls a specific device. For example, if it is a monitor, we call it as monitor display controller. If we have a printer, we can call a controller which controls how the data is handled in the printer. Apart from that, in the device itself we have a lot of memory, call it as small size memory, we call it as registers. These registers will have memory that is pertinent to individual device, that has information about the status, the control and the data. So, you can store data in the data register, you can show the status whether it is printing or idle in the status register, and the control register which gives instruction to be done. Then we have the device driver, that is very important software module controlling the device. So, for any device which connect as an output device or a network device, we need to install a separate driver software that controls the particular device. So, we all know that if you buy any electronic device, the device will be accompanied with a driver that contains how this driver can understand the request generated as a uniform global request. So, this is about components of I/O. Of course, these components are connected like this. So, we have input device and we have the output device in between, the CPU which contains the control logic unit which generates control signals, and arithmetic logic units which process it based on the control units output and instructions. Then we have the registers which are used for retrieving the instruction from the memory, and at last if you want to put that in a particular output device, you can send that to the output device. So, this is overall component. The various device drivers, the kernel will act as the base for interaction with the device driver and the components, device output devices. The kernel modules that manage device operations, it translates the OS I/O request into device specific commands. So, this is the main purpose of device driver. So, OS will say print or it says send. So, printer we have different types of printer. For example, if you connect a printer, the printer will be installed with the driver software. If you change the printer, the same driver will not work, because that printer will have different specific I/O commands to perform. So, we have to change the driver software. So, the I/O only will enable this, and the driver's main responsibility to initialize, transfer data and handle error. So, these are the main responsibility of a device driver, provides abstraction over the hardware details. So, it will interact with hardware, but that complexity of the hardware deployment is not revealed outside, it is not necessary for the device. We can handle this I/O in different forms. One is about interrupt driven I/O. So, this interrupt driven I/O is CPU can perform some task, and an interrupt will be generated by the device. Based on this interrupt request, the CPU will give attention to handle this I/O. After completion, the CPU will continue. So, if you look at this diagram, you can see first one, the device driver is initiating an I/O operation. So, this I/O is of course, CPU will be running executing some instruction. So, if device driver initiates I/O, this I/O controller will check whether the input is ready and output is complete or error handles, generates interrupt signal. This interrupt will go to the CPU. Upon receiving this interrupt, the CPU will transfer this interrupt control to the interrupt handler. So, we have the interrupt handler that will have a routine for handling this interrupt. So, the interrupt handler processes the data and returns from the interrupt, and CPU resumes processing of the interrupt task. So, if any interrupt occurs, the interrupt controller will assign this task to the interrupt handler. The interrupt handler will do this, and after completing this, CPU will resume from where it is left. This is one form of handling I/O. The another is the interrupts CPU the interrupts will improve the CPU utilization. That is the main thing. Because we have a separate handler that can handle the interrupt. There is a concept of direct memory access that reduces the CPU involvement for large transfers. So, it will acquire the permission and it acquires the resources for data transfer, and it performs the data transfer, and CPU may be doing some other task which is very much computational based, instead of having transfer or I/O based. So, the kernel handles this interrupt handling routine. So, this interrupt handling routine is very much essential for handling the interrupt without much involvement of CPU. The DMA setup and synchronization will enable the CPU to perform other tasks rather than doing simple input and output, which is a time consuming job. So, as far as the value of the CPU cycles, performing I/O requests with the CPU cycles is very low. So, how DMA plays a role in performing I/O? With this diagram we can see, for example, we have the DMA controller, which we have the I/O devices connected with the DMA controller, and if you want to perform any I/O operation, so it will generate a request to the CPU. We call it as bus request. So, it is asking for bus I need bus for performing the operations, it is asking for bus to the CPU. So, CPU will issue a bus grant signal. Once the bus grant signal is done, then we can use the address data bus to access data from the memory or to the memory and to the I/O devices. So, the DMA controller plays a major role here, which enhances the performance by not allowing the CPU to, it is not allowing CPU, it is getting permission from the CPU to perform this operation, thereby CPU can do some other operation. The performance of the CPU can be increased if you use this kind of I/O transfer. So, basically the kernel I/O subsystem services are listed here. So, first is I/O request scheduling, the second is buffering, caching, spooling, error handling and I/O protection. So, we have different tasks of kernel I/O subsystem. So, if you look at the I/O scheduling, it determines the order of I/O request servicing. For example, if I want to, if I receive request from 3 processes to access some data in the disk, for example, the read and write head of the disk is, one request is asking for a data which is at the middle of the disk, and the another process is requesting data at the end of the disk at the last sector, and another request is coming to retrieve this data in the first block. So, middle, last and first. So, if the order of the request is not scheduled properly, if you go with middle, then first, then last, then the head should move from middle, then from middle it has to go to first, from first it has to go to last. So, from first and last it is a tedious mechanical movement that is happening in the disk. So, in order to avoid it, we have to rearrange the order of giving request. For example, if it access the middle one first and the second last and third, automatically the head will go from the first if you apply appropriate scanning scheduling algorithms. So, here we have listed first come first serve, shortest seek time first, scan and C scan, which we can choose based on the requirement. So, ultimately it increases the throughput, response time and fairness. Choose appropriate I/O scheduling algorithms that can enhance the performance of I/O. That is the one service by the kernel. So, kernel will decide all this, choosing the appropriate sequence of handling the input output requests. So, this is one thing. It gives us algorithms for, as mentioned here, first come first serve, SSTF, scan or C scan based on the request. The second is buffering. So, this is one service of the kernel I/O, the kernel which says that temporary storage used during I/O transfer. So, here one process is generating data and another is doing printing or something, for example. So, what will happen if you use a common buffer, it has to feed in the buffer, the device would wait till the buffer is filled. When the buffer is filled, then process should wait, data from the buffer is taken by the printer and printing it. So, printer has to wait or the process application has to wait. So, instead of, to avoid this process, we can have a dual buffer where one buffer can be used for filling the data. Once the buffer is filled, then this buffer can be assigned for printer to print, and the second buffer can be used by the application to fill the data. Once this is filled, the printer can print. So, alternately we can do, this is called double buffering. So, we can have types like single buffering, double buffering, circular buffering. All these buffering mechanisms can increase the speed. If you use a single, there are items where we can have a single buffering can be used, but in cases which I explained now, double buffering may be appropriate. So, I/O devices will send data in, operating system will handle that, it moves to the user process. This is single I/O buffering. So, I/O device sending data, then it is moving that to the user process from the keyboard to the system. So, I am giving input to a program. Once I compile and execute, I can give input. This input is single buffering. If I give, it will go directly. The second is double buffering, which I said about printing. Buffer is overfull, it will, the process rotates, keeps sending and receiving data. So, this is one mechanism which kernel I/O playing a major role. The next is caching. So, caching we all know it is frequently accessed data is stored in the fast memory. It reduces the disk access time. So, the caching is managed by the kernel. Caching always stores data belonging to various items which needs in quite short time. So, commonly used in file system and block devices. So, in the diagram you can say that we have the cache memory sitting in the CPU. So, this cache will contain the data which is currently required by the CPU for next short duration of time. It is about it is about the prediction of future requirement that can be kept in the cache memory for faster access. The next is spooling. This is used for shared devices like printers, where output stored on temporarily on disk, device processes job sequentially, prevents conflict between multiple processes. So, here spooling is many processes will send data to a printer for printing at the same time, but printer cannot print data at the same time for all the processes. So, what it will do? It will put that in the spool, and based on the spool data it will generate output for each process. So, this spooling concept is mainly used in places where we have shared devices. So, we have a printer connected with multiple systems. More than one system generates data for printing. The printer will apply this spooling concept for. So, it will temporarily store that, and the order is maintained, and the document which is printed is with respect to a particular user. So, it will not give data that is accepted from a particular client to another client as output. So, no. So, in order to retain the independency of the client data, and also it will maintain the order. This is spooling is one of the services by the kernel in terms of handling I/O. Error handling, yes, of course, we have a lot of issues while doing I/O. So, one issue is hardware failure, example printer out of paper, disk not properly fixed or whatever. So, transmission error in terms of sending data in the network, and timeout of the device, device is idle and idle device comes out. So, the kernel will do all this handling, retry operation, report errors to the application saying that this I/O is not able to complete, and can have a log of all the error values for diagnostics and recovery from the error. So, this is also one major service by the kernel subsystem. The next is I/O protection and access control. So, it prevents the unauthorized device access. For example, if you want to print a document, you have to enter the password. Yes, you can have a device level authorization. The technique using privileged instruction, user and kernel mode operation, device access permission. So, here the device access permission will say that you are allowed to take a print, and we have a user level and kernel mode separation, where the kernel will have super user privilege and users are less privileged. So, we can have that. So, we can use instruction level privileges also. All these techniques can enable security and protection for I/O access. So, overall it enables the stability and the security for the system. Now, we are going to see about I/O streams. So, I/O streams are it provides the independency about what type of device you are going to use, and what type of data you are going to generate. So, abstraction representing a flow of data. So, we have framework in Unix like streams itself. So, that will accept data in the form of a stream, and it produces the output. So, data flows sequentially. The stream based I/O hides the implementation details of the device, and it is commonly used in Unix kind of systems. Of course, we have other systems also. We have streams concept. So, if you look at this diagram, you can see the source input data stream is generated, and the processing unit like streams. That stream is like this. It is a framework in Unix. These streams will do processing, and in case of error, it generates error or it generates output data stream. So, from the source you pass that to a stream framework, then it will give to the destination. In case if there is any error, it will generate error report. So, different types of I/O streams. First is input stream, read data into a program. So, it is reading data from the user keyboard or whatever into the program. Output stream is write data from the program. So, if program is trying to send data outside, it may be data to a printer or to any device. So, bidirectional stream is supporting both read and write. You get input as well as you give output the same device. So, examples of all we have standard input SDIN, we have standard output and standard error. So, these are all the different types of I/O streams, getting input from the keyboard, giving output to the standard I/O out device, and handling the error messages. So, the kernel supports these I/O streams in terms of mapping that with files, devices, pipes, sockets. All these are all different types of handling I/O with respect to different process, with respect to a process from one system to a process to another system via socket. So, kernel manages all this I/O transfer between two processes, which is running the same machine on the different machine. or between two devices in the terms of stream buffering, synchronization and resource allocation for handling this I/O. So, it enables uniform read and write operations for handling data generated by the applications to various devices. So, as a whole we discussed about the kernel I/O subsystem, which is the vital for system performance, which handles the input data as per the requirement for the devices, and also the handles the independency of the various devices, and also provides the abstraction between the device and the application generates data. It provides abstraction, efficiency and protection for the data. I/O streams simplify application level data, which generates data in the form of a block, in the form of a stream, in the form of a character. All this can be handled by I/O. Together they enable reliable interaction between the software and the hardware. Understanding the various I/O mechanisms, either it is interrupt I/O or DMA based I/O or programmed I/O, all this will have a major impact in OS design and optimizing techniques for handling this input and output. With this, this presentation is going to end, and I thank all of you for listening this lecture. Thank you.